Hi everyone, my name is Joe and I'm part of the Bath Open Instrumentation Group at the University of Bath. Our main project is the OpenFlexure microscope. The OFM is a low-cost open source microscope 3D printed in plastic, and depending on the user's budget and interest, the microscope can be customized for a number of uses. The lower cost versions can be used in outreach and education, and we're organising workshops in schools for children to build our microscopes in science and programming classes to support the national curriculum. We also offer a lab grade version with a cost of parts around $200 US, including the high resolution optics, a Raspberry Pi and stepper motors to precisely move the sample. This setup has applications in research and healthcare, and these microscopes are being manufactured by our collaborators at Bongo Tech and used to image blood samples at the Ifakara Health Institute in Tanzania. The reason we're developing with healthcare professionals is the OpenFlexure microscope's potential in supporting the diagnosis of malaria. The World Health Organization describes manual optical microscopy as the gold standard of malaria diagnosis. In low resource areas, access to microscopy is limited because of the need for expensive microscopes, trained technicians, maintenance, and an international supply chain. Locally manufacturing a low-cost, portable and digital microscope removes many of these issues, which is why we're developing the OpenFlexure microscope from an academic prototype towards being a certified medical device for point-of-care malaria diagnosis. This overall research objective directs the majority of work we do on the microscope. Rather than focusing on continuing to add features and options to an academic prototype, going through certification requires a shift of priority towards producing a reliable, accessible device. We need to make sure our stakeholders, from the development team all the way through to international manufacturers and end users, understand the decisions we've made, the likely points of failure, and how best to prevent these failures from happening. A major step we've taken towards this is the beginning of our failure mode analysis, or FMA. An FMA is a systematic review of every stage of the design and manufacturing process, looking at how the microscope can go wrong, why these failures happen, how long is acceptable before the failure is likely to happen, and how severely the failure would impact the user or manufacturer. Answering these questions helps us to come up with a clear plan on how to prevent or limit each failure as much as possible. Along the bottom, you can see an example of the FMA, assigning scores to how severe and how likely a failure is, how long is acceptable before this failure occurs, and the severity multiplied by the likelihood of the failure occurring, which gives an overall risk score for each failure. This score helps us to reprioritize our work by systematically addressing the most important failures. An example of this is in the microscope hardware design, in a change we made to the stage that holds the sample in place. The FMA identified a failure that screwing directly into these printed holes can strip the threads, which affects how the sample is held in place. Initially, this sounds like a minor issue, but the FMA flagged it. It's a fairly common failure, it can be easily done while manufacturing the microscope, and because the microscope body is printed in a single piece of plastic, the impact is that the entire microscope body would need to be reprinted and replaced. This combination of a likely failure with a severe impact is the highest priority for the development team, and so we redesigned the stage with this nut trap to make the microscope easier and less risky to assemble. The FMA and considerations of failure modes isn't just for the hardware, it also applies to the software that we include with the microscope. On a manual microscope, hardware and sample imperfections as you travel around the sample mean that the system can easily lose focus. A microscopist can fix this by regularly moving the optics up and down to find the focal point where the image is sharpest. And an automated microscope needs to be able to replicate this process moving the optics compared to the sample to maximize the sharpness in the image. With the 100 times magnification objective that we use for blood scans, the range that the microscope is fully focused in is less than a micron, or 1/1000th of a millimeter. This is where the precision stage of the OpenFlexure microscope becomes essential. To demonstrate the idealized way that autofocus could work, imagine moving the optics towards a sample and measuring the sharpness. Once you identify the sharpest point, you found the focal point, and you can move the optics back to that point to collect a sharp image. Or for blood samples, you can start collecting what we call a Z-stack. Move below the focal point and take an image, then move back up in regular steps, taking more images. The central image in this stack will be at the focal point you found and will be the sharpest, and you can use this for diagnosis. The other images in the stack can be used later to assess how well the system focused. If you tile 100 of these central images together, you can have a large area recreation of the blood sample. A technician can then search this for parasites and diagnose the patient without having to manually collect 100 images. But if the autofocus fails at any point, or there's a problem with the capture, the procedure would be taking information away from the healthcare professional, making a confident diagnosis more difficult. Once the microscope and sample have been moved away, it's difficult and time-consuming to return to the area with the issue and retake the images, as well as being disruptive to both the user and ultimately the patient. So let's repeat this procedure with the same attitude that we performed the FMA with. We're measuring the sharpness across a range. How do we choose this range? And out of all of the sharpness metrics available, which one do we use? How well do we understand when this metric works and why? And when do we expect it to fail? What if we don't find a peak in the range that we search? Or if the peak we find doesn't look the way a peak at the focal point of a blood smear is expected to look? Once we've found a peak that we're confident in, do we want to move directly back to this focal point? Or is there a better order of movements to mitigate for minor imperfections in the movements? How can we limit the effect of backlash and ensure precision to within the focal range of 1 micron? Once we've collected an image, can we assess if there's a problem with the capture and quickly correct for it while the microscope and sample are still in that position? Can we use the sharpnesses that we've measured to test if we've really returned to and centered on the focal point? This is something we're currently improving, and to make sure users can have confidence while leaving the OpenFlexure microscope to collect hundreds of images for them. Finally, how reliable and clear is our documentation? Is it clear what's required of the manufacturers so that the design can be replicated by users without needing to contact us directly? Is the liability of using a locally produced medical device well understood and accepted by every partner at every point of the process? What's key for us to work towards is that certification isn't and won't be awarded just for the design, it's awarded for the finished product. The manufacturer's procurement, assembly, fabrication and quality control procedures are all assessed as part of certification, and the decisions and limitations of the device need to be understood fully by the manufacturer. The documentation that we share isn't just the set of assembly instructions. We need to make it clear the decisions we've taken and how to modify the design if it becomes necessary. For example, here you can see the code used to print the microscope. If these variables and procedures aren't clearly defined, then regardless of our design and instructions, no one will be able to modify it. Taking these lessons forward, what's next for our project? We want to continue to develop the OpenFlexure microscope as a tool for education, research and healthcare, developing more options such as a greater range of motion and phase contrast imaging. But we'll also be developing the medical version to be reliable and suitable for local manufacturing around the world. We'll continue to collaborate with developers, manufacturers and end users to make sure that everyone's expertise directs the final product, making it suitable for Tanzanian health clinics instead of focusing on performance now labs in Bath. We'll continue working on the FMA, using it to prioritise our work. We'll also maintain it because certification in a successful project requires the FMA to be a living, active document, not just an exercise to be completed and forgotten. As well as looking forward, I'd like to look at the lessons we've learned as we developed this microscope into a prototype used around the world and now towards medical certification. It's a combination of steps that worked well for us, lessons that we learned later on to improve our workflow, and advice we'd give to similar projects looking to develop an international network. Firstly, wherever possible, collaborate with the stakeholders at every stage of development and in every location you hope to work with. Don't underestimate the amount of time required for full open discussions with partners, and wherever possible, move the discussions online and assign time to them. This way, the end users and manufacturers direct the design as early as possible, and any decisions made are agreed on and understood by all parties involved. Once a project moves past the prototyping stage, keep the original development team involved wherever possible. Avoid the mindset of having one team for innovation and prototyping, another for development, and another for reliability and certification. Often the prototype team will have worked on or rejected ideas and options that another team then wants to investigate. If you can avoid this duplication of work and understand why a certain path was chosen, development becomes a lot more streamlined and collaborative. If you're hoping that your project can be useful in other areas and settings, engage with collaborators there as early as possible. Local knowledge will help you identify the opportunities and restrictions there much more than any distance research you can do. And making societal and economic impact is important when typically during product development, you'll see a dip in academic impact. Finally, make sure your decisions are focused on the objective of your project. If your aim is very specific, don't try to force a generic solution or try to score highly in an arbitrary success metric simply because it's used elsewhere. Take control of your project and make sure that your development is leading where every stakeholder at every stage is hoping for it to go. If you're interested in the microscope, our project, or anything I've talked about, I'd like to encourage you to join the conversation online at openflexure.org. Thank you all for listening, and I welcome any questions.